Networks are everywhere. So we have, for example, social networks, road networks, collaboration networks, and so on. And one of the tasks we're really interested in performing is causal inference, and specifically figuring out how the behavior of an individual in a network is affected by their peers. And there is actually a lot of work going on right now that's trying to handle this task. However, the vast majority of it focuses on homogeneous networks. And what this means is networks with a single type of relationship. So for example, if you think of a social network like Facebook, we tend to think of it as people are friends with other people. And that's it. We only have friendship. However, in practice, networks are heterogeneous. They can arise from multiple types of relationships. So going back to the Facebook example, people have friends, they have coworkers, they have relatives, and each of these sets of peers can possibly affect you in different ways. So in this work, we study what is the impact that the presence of different types of relationships has, specifically for the task of causal inference on networks. So in this talk, I'm briefly going to give you some background on causal estimation specifically for networks, then move on to see how these concepts can be applied and extended to the case of heterogeneous networks, and finally present some results first on synthetic data, and then an application on a real-world data set. So let's start with causal effect estimation in networks. So say we have our social network, so we have a set of users, they're friends with other users. So we have a population of n individuals that are not independent. They form a graph. And without loss of generality, let's assume we have two features we care about, a binary treatment and some outcome. And in this setting, the outcome of a node doesn't only depend in their own treatment, but also in the treatment of their peers and more generally of the entire network. Right? So how's your outcome going to behave depends on the treatment that you received and the treatment that everyone else received. And the quantity we care to estimate in this case is the average treatment effect between global treatment and global control. What this means is that ideally, we would like to take our social network, assign everyone to treatment, measure their outcomes, and in a parallel universe, take the exact same network, the exact same time, assign everyone to control, measure their outcomes, and then compute this average treatment effect. And as you can see, this is something that we cannot possibly ever observe, so we need ways to estimate these things. And generally, causal effect estimation works in three, let's say, steps. The first is treatment assignment. So deciding who's going to be assigned to the treated group and who's going to be assigned to the control group. So if this is an experimental study, this is part of your experimental design. If it's an observational study, there is some external mechanism that takes care of treatment assignment. The second step is figuring out when do we consider someone to be treated. Now, in a non-network setting, if you have independent individuals, this is almost simple. So if you receive treatment, you're treated. If you didn't, you're in control. However, in a network setting, this becomes more complicated. So for example, in a network, maybe you are considered to be treated if you received treatment and all of your peers did as well, or X% of your peers, or at least one of your peers. So all these decisions that you need to make constitute your exposure model. And the final step is the analysis. So how do you take all this information and combine it to actually compute the quantity that you care about, to estimate an average treatment effect, for example. So for this talk, I'm going to focus on an exposure model, the fraction neighborhood exposure model, and the linear regression adjustment. And these are concepts that were introduced by Gui et al. In their paper in WWW in 2015. So a little more details on these two concepts. I'll get this. Great. So the fraction neighborhood exposure model, what it says is that the response function of a node is going to be a function of two things, their own treatment and the proportion of the treated peers. So for simplicity, they model it as a linear function of these two quantities. And what's neat about this is that with this response function, your average treatment effect is simply the sum of betas and gammas, where beta is the effect from your own treatment, and gamma is the effect from your peers. And betas and gammas can be estimated from data, in this case with a simple regression. So this is great and works for the case of homogeneous networks. Now the question is, what happens when we have multiple types of relationships? So when we have, let's say, a social network with friends and coworkers. So in the case of the homogeneous network, the response function that I showed you earlier is the linear function of the treatment and the proportion of the treated peers. In the case of a heterogeneous network, a possible response function is the one that I'm showing on the bottom. So maybe it's a function of your own treatment, the proportion of your treated friends, and the proportion of your treated coworkers. But at this point, you might realize that there are more options than just this, right? So actually, you have all these combinations of sets, friends only, coworkers only, both friends and coworkers, and so on. So what happens in these cases? So what we did in this work is we considered 5 of these possible models. And the reason we picked them is because we thought this is what intuitively a researcher might do. So here is a visual representation of these 5 options we considered. So the first one is just friends. So basically, ignore the one type of relationship and only consider the friends of a node. The second one is the reverse, so ignore the friends and only consider the coworkers. The third one is maybe a naive approach, so just ignore the type of the relationship. If you're a peer, you're treated equally. It doesn't matter if you're a friend or a coworker. Then we consider what we call a disjoint model, where you take the most fine-grained approach that you can. So you model every non-overlapping set separately. And finally, we considered a model where you consider the friends, you consider the coworkers, and what happens intuitively here is that people that happen to fall in the intersection, that are both your friend and your coworker, you implicitly account for them twice, so they will have an additive effect on you. So how do we use these peer sets of interest? So we use them to define the response functions. We use them to define the corresponding estimators for the average treatment effect. And since we're going to be generating data synthetically, we also use them for outcome generation. So let me give you a more concrete example of how this works. So say we have this model with our friends and our coworkers. The response function that will be defined for this model will be a linear function of a node's treatment, the proportion of the treated friends with a coefficient gamma f, and the proportion of the treated coworkers with a coefficient gamma c. In this case, the corresponding estimator will be the sum of these coefficients. And if we were to choose to generate data based on that model, here's how it would work. It would be a function of your treatment, a function of the outcome of your friends, and a function of the outcome of your coworkers. Great. So we have defined all these maybe complex notions and sets. And now the question we actually do care about is, what do we do with this? Do we care about this? What does it happen when we ignore all this extra information or we misspecify it? And specifically, what happens for estimation of treatment effects? So to answer that, we ran a set of synthetic experiments. So first, we generated graphs, and we used 3 different graph generation models. We basically generated random graphs, small world networks, and then graphs using the stochastic block model. So for each one of these, we generated 100 graphs with 1,000 nodes. Then on top of the graphs, we generated values for the treatment. And we did this in 2 different ways. The first one was an independent assignment. So basically, go over your network. For every node, flip a coin, and with probability p, assign them to treatment, 1 minus p, assign them to control. And the second way to do this using graph cluster randomization, effectively what this is you first form clusters on your network, and then you assign treatment on the cluster level. So for every cluster, you again flip a coin, With probability P, you assign everyone in the cluster to treatment. 1 minus P, everyone in the cluster goes to control. And the reason this has been used is because it has been shown to reduce the variance of your estimators. And now that we have the graphs and the treatment values, we generated values for the outcomes. And again, we used two different approaches. The first one was to have the outcome to be a function of your treatment and the outcome of your peers. So effectively, this defines a diffusion process over the network on the outcomes. And the second one was treatment interference. So now your outcome is a function of your treatment and the treatment of your peers. So as you can imagine, this gives us many configurations. I'm not going to show you the results for all of them. To start with, I'm going to show you results for just one of these configurations. So when the graph was a small world network, the treatment assignment was done using graph cluster randomization with probability 0.5. And the outcome generation was done using treatment interference. And here's what the results look like. So on the x-axis, you have the true model that we use to generate the data. And on the y-axis, you have the assumed model. And the numbers I'm showing you is the relative bias of the effect that you estimated. So it's the bias over the true ATE. So in the secondary diagonal, you basically have the cases where your true model matches the assumed model. And unsurprisingly, this is where you have the least relative bias. What might be more surprising is how much worse you might do if you do not assume the correct model. So for example, if your correct model was the disjoint one and you only considered the friends, you might be up to almost 50% off on the estimated treatment effect. And now, just to give you a more high-level view of the results. So this is the configuration we had before for what I showed you. Now I'm just going to show you the results where the treatment probability is not set to 0.5. Instead, it varies from 0.1 to 0.9. And here's a very pretty graph. I'm very proud of this. So the different facets give you the different generative models. On the x-axis, you have an increased treatment probability. And again, on the y-axis, I'm plotting the relative bias. So ideally, what you want to see, every line in one of these graphs is a different assumed model. What you want to see is the line whose color matches the color of the title to be at 0. That means, or close to 0, that your assumed model has a relative bias close to 0 when it matches the generative model. And this is exactly what is happening if you see across the plots. Now, at this point, there are a few trends we observe that warrant further investigation. So for example, the disjoint model, the orange line, the relative bias in absolute terms tends to increase as we increase the treatment probability. So at this point, we have shown that using different semantics does make a difference on the values of the effect that you estimate. And the next question is, great, can you tell us which one should we be using? So given a set of candidate models, how can we pick the one that is a true one or at least more closely matches our data? So we choose to treat this as a model selection problem. And effectively what it means is we have the same data sets that we generated before on synthetic graphs and synthetic data. Now for each of the 5 models that we're considering, compute the Bayesian information criterion, which basically gives you, it's a score that tells you how closely your model describes your data, penalizing for the complexity of the model. And then select the model with the lowest BSE, which is the better fit. And the results for these experiments, so we have the 3 different types of networks we generated. On the x-axis, you have different configurations of coefficients, which is the relative importance between friends and coworkers that we considered. And on the y-axis, I'm plotting the accuracy of model selection. So how often BIC would actually give you the true model that generated the data. And the color corresponds to varying noise coefficients. Now, it's worth pointing out that the baseline for random here is at 20%, 1 out of 5. So model selection with BIC does better than random always. And we notice that the accuracy does depend on the topology of the network. So it's doing better for graphs generated with the Watt-Strogatz model, so small world networks. And it's doing worse for random graphs generated with Erdos-Reyni model. It does depend on the noise, which is to be expected. So the more noise you have, the less accurate your model selection. And it does depend on the configuration of coefficients. You can think of it as the configurations go from left to right. What effectively is happening, the friends and the coworkers become more and more distinct. So the more distinct they are, the easier it is for us to distinguish which semantics to use. The next step was to try to apply these concepts on real data sets. So we found this data set it was collected from a study on the diffusion of microfinancing in villages in southern India. So effectively what they did is they went to 75 of these villages and they conducted village level surveys and individual level surveys. And every person there identified 13 different types of relationships, of ways in which they interact with their peers. So that included friends, relatives, who do you go to temple with, who do you watch TV with, and so on. And on top of that, they had demographic information on the individuals, like the gender, if they're working, their education level, and so on. So in this setting, what we did is, before I go there, so this is the social network of one of these villages, just to give you an idea of how it looks like. So the green edges here correspond to friends. The yellow edges correspond to relatives. And purple edges are people that are both your friend and your relative. So you see there is a great overlap between the two different types of relationships. And the social networks for the rest of the villages were similarly looking, also for almost every pair of any two relationships. Now, what we did is we considered several pairs of relationships, like friends and relatives, and several combinations of treatment and outcome values. And for each one of these combinations, we estimated effects using the 5 different models that I presented earlier. And here are the results of this analysis. So on the x-axis, you have the different configurations, pairs of relationships, and pairs of treatment and outcome. And on the y-axis, you have the magnitude of the estimated effect. And the different colors give you the different models that we assumed. Now, you will see that the different models do have a role in the estimated effect. And what's more surprising is that in one of these cases, the sign of the effect changes depending on your model. So 2 of these models think that the treatment has a negative effect on the outcome, and the other 3 that it has a positive effect. Now, at this point, I need to point out that this data set is an observational data set. So these results should not be, at this point, interpreted causally. So we haven't performed an experiment. We haven't accounted for all possible confounders. This is just to showcase that the different models that you can assume in heterogeneous networks do have an effect, and we should be really careful on the analysis that we're performing. So to sum up, there is currently a lot of work in causal inference for data produced by networks. And in this work, we address the case of heterogeneous networks and how causal effect estimation can be adapted for these cases. We have shown that these intricacies of the semantics do have an impact, and misspecifying the relational structure of the dependence can significantly bias estimates. And we have also shown that using model selection techniques can actually be used in this setting in order to choose the appropriate semantics, the appropriate response functions. Now, that being said, there are a few interesting directions for future work. So first of all, characterizing the bias and the variance of these estimators. Now, we can consider more complex response functions. So for example, we can have effects that are present for multiple types of relational phenomena, homophily, contagion, longer range dependencies, and so on. Moreover, we used BIC for model selection. It would be worth investigating what you can do with model selection techniques that are customized for networks or relational data. Maybe that will improve the accuracy of model selection. Also, these methods can be incorporated in a fully automated framework that will allow you to choose from all the possible semantics by exhaustively enumerate them. And finally, it opens up questions about A/B testing in the case of heterogeneous networks. So how can we design experiments, how we can assign treatments in networks with multiple types of relationships, so that we can robustly infer causal effects in these settings. And I'd be happy to take any questions.